Okay, I think it's 2 minutes past 2 o'clock, so maybe we should get started. So I'm Radu Balan. I'll be introducing the speaker and moderate the talk today. We plan to record this entire talk, and actually the recording has started, which means that if you like your face not to show up on the recording, feel free to turn off your camera, turn off the microphones, use the chat to ask questions, for instance, if you don't want to interrupt the speaker. I will monitor the chat box, and as time goes by, I will interrupt and ask the question. Okay, so it is my great pleasure to welcome you all and welcome the speaker as well to our first CSCAMM seminar this semester and new academic year, especially in this new format, the online, fully online CSCAMM seminar. So our speaker today is Professor David Jacobs from Computer Science, University of Maryland. And just a few words about his background. So he obtained his Master of Science and PhD in Computer Science at MIT in 1992. So he spent the following 10 years, 1992-2002 at NEC, that's Nippon Electric Company. That's a research lab located in Princeton, New Jersey. And as a side remark, chances are that during those 10 years, well, at least maybe for 3 years, we might have crossed our paths on that area because I was working at Siemens Corporate Research, close by lab, walking distance from the two buildings. From after NEC, Professor Jacobs spent a few years in various places visiting, among other things, the Royal Institute of Technology in Stockholm, École Normale Supérieure de Cachan, and ETH in Zurich. After joining University of Maryland, he had a very strong group in machine learning, computer vision. And recently in 2018, he was named, well, the interim director of the Machine Learning Center for Machine Learning, but I believe he's actually currently the director of the Machine Learning Center. Today, Dr. Jacobs will talk about frequency bias in deep learning. So without further ado, please, the microphone is yours.
Thank you, Radu. Yeah, and please interrupt with questions at any time, and we'll try to keep track of the chat and answer them as they get asked. Yeah, so thanks a lot for having me. And I'm going to be talking about a series of pieces of work that I've done with some collaborators in the last year and a half. And this is described in 3 papers we've recently had. And let me just give a sense of the high-level goals of the work before I start talking about the details. So the basic goal when we started was to better understand the inductive bias of deep neural networks. What kinds of functions are easy to learn or are difficult to learn with a neural net? And when you have overparameterized networks that might learn many functions to fit the data, how do we figure out which functions they're going to learn? And when we started working on this, we became aware of this very nice work on the neural tangent kernel, and we built on this work. What that prior work does is it shows that if you have a very overparameterized network, you can linearize it. And so you can view what the neural network is doing as a linear system, which makes it much easier to analyze. And so based on that model, we're able to understand the inductive bias of the neural network, assuming, making some assumptions. And that was really interesting to us. But then also, we're able to figure out how to compare neural networks, which can be represented by this linear system, to other kernel methods that are already around. And kind of surprisingly, we find out that, at least for the case of fully connected neural networks, and this is not true for convolutional networks, but for fully connected neural networks, they can perhaps be very well approximated by some classical kernel approaches. And so I'll try to explain that. All of this work has been done in close collaboration with my longtime collaborator, Ronen Basri, who's a professor at the Weizmann Institute. And we've worked with a bunch of his students, Amnon, Yoni, Shira, also with Marav Galon, who's a research scientist at Weizmann, and with my own student, Abe. So you probably all know that there's been this revolution in deep learning, which is completely dominating AI now. And in particular, I come from the field of computer vision, and about 90% of computer vision these days is really applied deep learning, figuring out how to design appropriate loss functions and architectures of deep neural nets to solve vision problems. And so, one of the reasons that we're doing this work is that Ronan and I worked together on computer vision for a long time, and we'd like to work on theoretical problems. And now it seems that if you want to understand something in computer vision theoretically, the thing to do is to try to understand the theory of neural networks. And so one of the big, in general, when you talk to people about neural networks, there's always this kind of air of mystery where people almost view it as a kind of black magic, that you train these networks, they work great, they solve all these problems, but it's kind of a mystery as to why they work so well. And one of the biggest surprising things that's come out of neural networks is that they seem to contradict some long held wisdom in machine learning. And so in classic machine learning, one of the first things you learn is that you can't overparameterize your problem. You always have to have many fewer parameters if you're trying to fit a function to data. The number of parameters in your function should be much less than the number of pieces of data you have. And if you have too many parameters, that means there are going to be many functions that will fit your data, and you're likely to overfit and pick the wrong function. And people applying neural networks in practice just routinely break this advice. They use neural networks that have a huge number of parameters, tens of millions, 100 million parameters, even more sometimes, even though they might apply these to networks that have maybe 1 million training images or even fewer. And people have become very cavalier about this. There's people just don't even worry about having too many parameters in their networks anymore. And the experience has been that if you make your network bigger, it usually works better, even though in principle you might expect overfitting. And so one question is, why does this happen? And one's immediate intuition would be this must have something to do with the inductive bias of the neural network, that even though there are many different functions the network could be computing that would fit your data, somehow it's picking out a good function, a simpler function in some sense, a function that generalizes well. And that's one of the things that we wanted to understand. So just to sort of set up our viewpoint a little bit, I'm going to talk about a couple of experiments. The first one is due to Zhang et al., and this is from Ben Reck's group at Berkeley. And throughout the talk, I'll be talking a lot about work that other people have done, because we've really benefited a lot from the work of other people. And so they did this experiment, which got a lot of attention, but it's pretty straightforward. So there's this standard data set you've probably all seen called MNIST, which is handwritten digits. And normally these digits are labeled by the number of the digits. So this is really a 1, this is a 9, this is a 4. And people know that you can train a neural net and do very well at classifying these digits. And so what Zhang et al. Did was they scrambled the labels. They just assigned every digit a random label. And they showed that a standard network could also learn all of that training data. So it could essentially learn to memorize these random labels. And that is, it could overfit. And in a way, this should be no surprise. You expect that networks, that any learning mechanism, if it has enough parameters, can fit any data. And neural networks can. This graph on the right shows an interesting thing about the dynamics of this, though. So this blue curve, the leftmost curve, shows the sort of the learning rate for the standard data, which is correctly labeled. And you can see that very quickly the network learns to correctly label all of the training data. And this also extends very well to test data. The red curve on the right shows what happens when you train the network to learn these random labels, and it does it, but it's much slower. And so this sort of suggests that the random labels require a much more complicated function, and the network is learning this more complicated function more slowly. And so, perhaps this isn't really so surprising, but it says that something about the rate at which things are learned is important. So based on that, we did a slight variation on this experiment where we just took our training data, and for half the training data, we used the correct label, and for half the training data, we used random labels. And so if you look at the dynamics of the network as it's learning to fit this data, this shows the accuracy of the training data, the accuracy on the training data, and you can see that it pretty quickly gets half the training data right, and then more slowly starts to learn the rest of the training data. If you look at test accuracy of digits that have the correct label, so these are not noisy, these are all correctly labeled, then an interesting thing happens. Very quickly, the network that you've trained is doing much better on this test data than it is on the training data. So after just a little bit of training, we're getting about 50% correct on the training data and close to 100% correct on accurately labeled digits. And so what this indicates is that very quickly, the network is learning a function that accurately labels the digits. And then as you train more and more, you start to overfit. You start to fit these randomly labeled digits. And as a result, your test accuracy goes down because, and what this suggests is that there's kind of a correct function that labels the digits according to their true label. And then there's a kind of overfit function which just labels all this noisy training data correctly. And the network is first learning the correct function that labels everything correctly. And then slowly that degrades as it starts to overfit the incorrect training data. It learns a worse function. And again, this is consistent with the idea that the network is has an inductive bias that's causing it to learn a simple, and in this case, correct function first, and then more slowly learn a more complex function. And so let me just...
This graph is does the slope have a meaning?
You mean the slope? Oh, the slope of the red curve, or the slope of either of them?
Yeah, of either of them. I mean, or is it just this particular example and it's just the right trend?
Yeah, I don't think it really has a meaning. I think it really just means that it's very slow to learn the to overfit.
Okay.
Yeah.
Thanks.
Good. Any other questions right now? Okay, so and one thing that we wanted to look at, and other people have suggested this also, is that some of this bias might be understood in terms of frequency. And so I'm going to give an example now of learning a 1D function. And so here's a plot of the function we're trying to learn. And so you just think of so this is 1D, so a training example is just a one-dimensional vector, and that's the x-axis, and this is the label that it should have, the y-axis. And so we're just trying to train a network to learn this 1D function using the network for regression. So we use a loss function that's just a mean squared error. And this particular function is a combination of a low frequency and a high frequency signal. And so if you train this network for a little bit, if you train a network to learn this function for a little bit, the first thing it does is it seems to learn the low frequency function. And then as you train it more, it starts to learn the high frequency components of the signal. And ultimately, I'm sorry. Are you seeing the entire PowerPoint slide, or you're not seeing my screen with your images on it, are you?
We see 4 graphs here down below.
Okay, but you can see the whole slide.
I think so, yes.
Okay, good. I think if I shared my screen, that would not be the case. Okay, so good. So this shows also that the network first learns a simpler function and then a more complex function. But in this case, we can sort of make precise what we mean by simple. It first learns a low frequency function, and then it learns the high frequency components of that function. And so that's what we're going to analyze. And so we're going to look at where this frequency bias comes from and try to understand how long it takes to learn a particular frequency. And so, as I mentioned before, we're going to do this using this prior work on the neural tangent kernel. This is from a couple years ago, really just shortly before we started on this work. And the intuition here, so the idea of the neural tangent kernel is to linearize a neural network, so it can be treated as a linear system. And it can be proven that this linearization is highly accurate for the special case of infinitely wide neural networks. So that is neural networks with just a huge number of units. And the intuition here is that the wider your network is, the more units you have, the less the parameters have to change, the individual parameters have to change in order to fit a function. So if you have a huge network, you can change all of the parameters just a little bit during training. And so if you linearize the network around its initialization, because the parameters are changing so little, that linearization continues to hold. And particularly since neural networks that I'll be describing are computing piecewise linear functions anyway. And so literally when you linearize a piecewise linear function, as long as you're not moving from one piece to another, that's completely accurate. And the NTK shows that under these assumptions, these special assumptions, a neural network performing regression is equivalent to classic kernel regression. And we can understand the dynamics of the network as kernel gradient descent. And the kernel, the NTK, is given by, so that the value of the kernel for x and z is given by the inner product of the partials of the output with respect to the parameters with respect to x and z. And one way to think about this is that the neural network is computing a piecewise linear function. If x and z are very close to each other, then the function is the same linear function for x and for z. And so these partials will be the same. And the more different these partials are, sort of the more distant the points are in the topology of this piecewise linear approximation. And this is, inner product is an expectation over all possible initializations. And typically we assume the parameters are initialized, say, with a Gaussian distribution or something like that. Okay, and so I'm going to be talking mainly about the NTK for a two-layer fully connected neural network. So that's computing a scalar output. And so the input is just D plus one-dimensional vector. Every input value is connected to every hidden unit. And these are multiplied by weights and then summed up. And then there's a nonlinearity here. And then everything again is multiplied by weights and summed up. And so we can just write this as, for every input, we take the dot product of that with the weights leading to a particular hidden unit. We apply a nonlinearity sigma. We have another weight, AR, and then this is normalized based on the width of the network. And for theoretical, for reasons to simplify the theory, we assume that all of the inputs have been normalized so that they're unit vectors. And I'm just going to be talking about the sigma using the nonlinearity ReLU, which is just the max of x with 0. And this is the most commonly used nonlinearity in neural nets. And we're training this to do regression. And so we're just looking at the mean squared error between the label, the desired value, and the network output. and we look at that difference squared summed over all the training data. So this is just a standard regression loss. Okay, and so it turns out that we can write this as a linear system where the output of the network is just the weights times a matrix, Z transpose. And Z transpose contains all of the training data in it, as well as the nonlinearities. And so the idea is that when I multiply, say, the first row of Z transpose by the weights, ignoring these indicator functions, what this is doing is it's just saying, it's looking at how the weights are being applied to the first training example, and computing the subsequent values that are produced. And then those are multiplied by a nonlinearity and the weights of the second layer. And so the key thing is this indicator function here, which encodes the nonlinearity. So because we're using ReLU, if you take the inner product between x1 and the set of weights going from the input to one of the hidden units, if that's negative, then you need to make that a 0. And if it's positive, you leave it alone. And so this indicator function will just be 0 if that inner product is negative for the initial values of the parameters of the weights. And so this indicator function is just either 0 or 1, and that handles all the nonlinearities in the system. And so we're basically fixing those nonlinearities to be whatever they were at initialization. Okay. And then we can just think of backprop now, just this is the output of the function. So when we do gradient descent with this, it's just gradient descent with a linear system. And one interesting thing that we can show here, well, first, let me just mention that we can show that as the width tends to infinity, so what I've written down is just precisely true for the network at initialization and can become untrue during training as the nonlinearities change. But if the network tends towards infinity, then these nonlinearities don't change very much, and this becomes an accurate approximation of the network. And because this is a linear system, we can also show that it always has a solution. And so for any training data, the network will be able to fit that training data. We'll be able to learn a function that fits that training data. So to be more specific, we can think of this as a kernel method where this is the kernel. So this is for this kernel, we take an expectation over all the initializations. And when we do that, we get something that's just the dot product between these two different inputs, which is just the cosine of the angle between them, and pi minus the angle between them. And we can basically, I'll just sum this up without, these represent some assumptions that you can make. This is from a paper by Aurora based on work by Du previously. And these are things like just saying if the network is sufficiently wide and the gradient descent steps are sufficiently small, then we can bound the error in the function that we're learning as a function of time. We can see how many steps it takes. And so this allows us to understand how quickly a function is going to be learned. And the key thing here is that it depends on the eigenvalues and the eigenvectors of this kernel matrix. So if we want to learn a function that's one of the eigenvectors of this matrix, the rate at which we learn that function depends on the corresponding eigenvalue. Are there any questions so far? Okay, good. So this tells us that to really understand what functions the network can learn quickly or slowly, we need to understand the eigenvectors and eigenvalues this kernel matrix. This is the kernel matrix. We make one additional assumption now, which is a pretty strong one, that the training data is uniformly distributed. So because it's normalized, it lies on a hypersphere, and we're going to assume the training data itself is uniform on this hypersphere. This doesn't say anything about the labels. The labels could be anything you want them to be. But basically, we're saying that the training data uniformly samples the function that we're trying to learn. And this is an assumption that we relaxed in our second paper, and we looked at what happens when this assumption doesn't hold. But things are much simpler if you assume a uniform distribution. And in this case, the eigenfunctions of NTK can basically be shown to be, I mean, we just rewrite them and we can see that they're the eigenfunctions of convolution, which means that if we just have a one-dimensional hypersphere, a circle, the eigenfunctions of the NTK are the Fourier series, and in higher dimensions, they're the spherical harmonics. So we know what the eigenfunctions of this kernel are, and we can also compute their eigenvalues. So we can explicitly compute these, and there are two things to notice about this. One is that for even frequency, so here k is the frequency, right? So if you just think about the Fourier series, you can just think about it as the frequency of a cosine, which are the eigenfunctions. And for even frequencies, the eigenvalues decay at a rate of order 1 over k squared. For the but there's also a weird thing, which is that the odd frequencies are 0, which means that this kernel isn't actually able to learn functions that have odd frequencies in them. And it turns out that the reason for this is just pretty simple. It's because the network that I originally defined didn't have a bias term, which is an additive term for each hidden unit. And because of that, it's not actually a universal function approximator. It can't approximate functions with odd frequencies greater than 1. So just to illustrate that, if we just numerically compute the eigenvectors of this kernel, the ones with the largest eigenvalues are low frequency signals, DC component, low frequency even signals, and the eigenfunctions with the smallest eigenvalues are low frequency signals that have an odd number of, that are odd, that have an odd frequency. So this means that these two-layer neural networks, which have no bias in them, are not universal. And typically in the past, people have analyzed bias-free networks because they're just a little simpler to analyze. But it turns out that that's not really the right thing to do. You should really look at networks with bias, which I'll talk about in a moment. Now, this might seem to contradict something I said a few minutes ago, because I said this is a linear system and we can fit any training data. And that is true, but we can fit any arbitrary training data, but we can do it in a very weird way because we lack these odd frequencies. So here's an example of a signal with an even frequency and some random samples. So imagine these dots are fed into the neural network. So these are just x values or angles, and they're given labels based on this even low frequency signal. And if you use the kernel to fit these, you get a function that looks like this. If you do the same thing with an odd frequency function, the kernel can still use its even eigenfunctions to fit this signal, but it does it in a crazy way with all kinds of high frequency components. So they're all even, but they're very high frequency. And so obviously this wouldn't generalize very well. We can also look at the convergence time and skipping the details, basically because the eigenvalues decay at a rate of 1 over k squared, the time it takes to learn a function increases with order k squared. That's for the even frequencies, and the odd frequencies, it never converges. You can't learn those. So one question about all of this is we're making some pretty strong assumptions to do this theory. And in particular, we're assuming that the network is infinitely wide. And so something we worry about a lot is whether this is actually relevant to real neural networks. And I think the jury is still out on this, but I'm going to present some evidence today that this theory, even though it makes very strong assumptions, seems to fit a lot of empirical data pretty well. And so here's one case in which we just take a harmonic function of a particular frequency and train a real neural network which has limited width to learn this function, and it's just not a super wide network, just 100 or 200 units. And we compare the empirical amount of time that it takes for the network to learn the function, shown by the blue squares, and the theoretically predicted values. And you can see that there's a pretty good fit between what a real neural network does and what the theory based on infinitely wide networks would predict. And these dots up here just show that it never learns the odd frequency functions. So this isn't just a peculiarity of the theory. A real network without bias isn't going to learn these odd frequencies. Any questions so far? Maybe I should pause for a second.
But just make sure this is for a single or a monocomponent signal, right? The k-index frequency, just
right.
one component.
A signal that just contains one frequency, k. And so the horizontal axis is the value of the frequency.
And the fact that you get this kind of a quadratic fit is because of the 1 over n squared, the Fourier coefficient decay?
Yeah, the 1 over k squared, yeah.
In lambda, right? Yeah, okay. Thank you.
Okay, so to fix this up, we need to add bias. And when we do that, the kernel changes a little bit. The only difference between this and the kernel I showed you before is this 1 and this normalizing constant. And when we do that, we get the more expected eigenfunctions, where we get first frequency 1, then frequency 2, then frequency 3, then frequency 4. And we also can analytically compute the values of these, and now we see that all of in general, the eigenvalues decay with 1 over k squared. And we can do similar experiments with the bias, and we also see a very good fit between the theoretical predictions and the measurements that we make. And we can also do those experiments all with a 1D signal. We did some experiments with the 2D signal. Because we're assuming uniform sampling, it's hard to go beyond a 2D signal. And it turns out that the decay rate is instead of 1 over k squared, it's 1 over k to the d, where d is the input dimension. And so in this case, the theoretical prediction is a cubic rate of increase in how long it takes to learn a function. And we see a very good fit to that empirically also. Okay, so this slide is just a weird peculiarity that comes out of this. So in this slide, we have some training data, and we train a real neural network to fit this training data and look at the function that's learned. So we're just trying to learn a function that passes through all of these points. And these points are constructed so that on the left and on the right, we can fit them with cosine of the same frequency. And so the question is, what would you expect to happen in between these two? And I mean, I think that 2 years ago, I would have said, well, it's going to somehow smoothly interpolate between these two. And what actually happens is the network learns a function like this. It learns a pure cosine function. And the reason, presumably, is because it can learn this function only using low frequency components, and even a smooth interpolation would have some high frequency components to it. And so because the network learns low frequency components of its signal first, it can just learn a pure cosine. And I have to say, it takes some fooling around to get exactly this result. If there's too big a gap, it doesn't do this. But to me, it's just kind of fun and very surprising to see a network interpolate in this way, which is not at all monotonic. Okay, so far, one of the big assumptions we made in our analysis is that the training data is uniformly distributed on the hypersphere. And that makes everything much simpler. But of course, in real life, you can't expect that to be the case. You expect your data to be clustered in different parts of the space. And particularly in a very high dimensional input space, it's not even clear what it would mean to have your training data uniformly distributed. I mean, you know what it means, but it's just not very meaningful. And so for the uniform case, what we showed is that if you have a signal like this, which is low and high frequencies, you first learn the low frequency and then you learn the high frequency. But suppose the data is not uniformly distributed. That is, you sample the function more densely in one part of the function than in another. So what happens then is something like this. So here we densely sample from the right side of the function, and we only sparsely sample from the left side of the function. And when we do that, the network in the beginning learns the low frequency approximation to the right side, and it doesn't learn much of anything on the left side. And then after some time, it starts to learn the high frequency components on the right side, and it's much slower in learning the low frequency components on the left side. And I think this is very intuitive. In the places where you have less data, you're going to learn more slowly. But we wanted to analyze this and try to figure out exactly what's happening. And so we wanted to look at the eigenfunctions of the kernel matrix when we have a non-uniform distribution of the data. And this is challenging, and so we've done this only for some special cases. The most important assumption we're making is that we're only looking at the one-dimensional input space. And this doesn't easily generalize to higher dimensions, I have to say. And so in that case, and a second assumption we're making is we're assuming, although the density is not uniform, so we're not uniformly sampling the data, that it is piecewise constant. So we can divide the input space into a few pieces or into some pieces, and the density is uniform in those pieces. And, which we can always do to some approximation. When we do this, we show that to get these eigenfunctions, we need to solve an ODE, and it's a little complicated, but we get the solution. And what this says is that the function that gets learned, the eigenfunctions of this network, are kind of piecewise cosines of different frequencies. So the cosine will be constant, so we'll have a constant cosine within a region of uniform density, and the frequency will depend on the square root of the density. So we can have an eigenfunction. Well, let me show this. So let me show what that looks like. So for example, here, this is an eigenfunction when the density is sparse on the left, much higher on the center, and then a little bit less sparse on the right. And so the eigenfunctions look like three different cosine functions pasted together. And where we have higher frequency in the center, where the things are more densely sampled. And this is also interesting because one thing this shows you is that if you want to learn a particular function to a particular level of smoothness, but your data isn't uniformly sampled, that it can take longer to learn a smooth function in one part of the data than the other. And so by the time you've learned, say, a frequency of 4 in data that has not been densely sampled, you may already be learning the 10th frequencies in the data that is densely sampled. And so it may be impossible to fit the sparsely sampled part of your data accurately without overfitting the part of the data that's more densely sampled. And in general, this is just showing how long it takes to learn a pure cosine function. And it just depends on this P of X star, which is just the density of the region that's most sparse. Right? So to learn a cosine, you're dominated by the least sparse part of your signal. And the eigenfunctions in S2 look like this, and this is very analogous to what I showed in 1D, where you have something that looked kind of like piecewise spherical harmonics pasted together. Okay, so this was to understand non-uniform densities. Any questions so far before I move on to the last part of the talk?
So Mike, could you show again the formula that relates the density of sampling points to the estimated frequency? So in that one, so does it mean that it's kind of reinforces your belief that if you believe that was a high frequency, so you sample with a higher, I guess, percentage, PJ, higher probability, higher density, you actually get a higher frequency component as well.
Yeah, exactly, right. So if you want to learn high frequency components in one part of your signal and low frequency components in another part, you could do this by more densely sampling the place where the frequencies are high. But, in a lot of neural networks, a lot of training sets, we don't really know where the high frequency or low frequency parts of the signal are a priori, and we just sample in some more arbitrary way.
Right. So I guess the question is, how do you actually balance the two things? I mean, your belief and then the fact that you reinforce the belief, but the underlying true signal might not be as you believe. Is there a way of correcting for that bias?
I mean, you can I guess you could correct for it by trying to sample more densely in the sparse part of this space, or doing data augmentation, for example. But to do that, you'd have to figure out what is the dense and what is the sparse part of the space.
Mm-hmm.
But it's an interesting point, because maybe, I mean, what it suggests is, for example, if you use early stopping, so you stop training when you start to overfit, there's a good chance you'll have underfit part of the space. And if you can figure out where you've underfit, maybe you can figure out a training strategy that then trains mostly in that part of the space.
Mm-hmm.
And we haven't looked at that, but that could be very interesting. Okay. Okay, so finally, since we're approximating a neural network with a kernel method and basically treating it as kernel regression, this raises the question of how does this kernel compare to existing kernels? And there were a couple of pieces of past work that make some points about this question. So first, there was this paper, which was pretty much experimental, by Sanjeev Arora's group at Princeton. And they did empirical experiments on the UCI dataset. So the UCI dataset is actually 100 different datasets. It's a standard dataset used in machine learning to benchmark different algorithms. And this is data that does not require convolution. So nothing I've talked about so far involves convolutional neural networks. I can make some comments about that if people are interested. But this is all fully connected neural networks. And this data set has been extensively experimented with. And the state of the art at the time this paper came out was random forests, RFQ. And so what this paper did was compare that, the results of random forests to the results of neural networks, which had already been done also, to the results of kernel regression with some other standard kernels, like a Gaussian or a polynomial kernel, and then the neural tangent kernel. And there's a lot of statistics here, but maybe just look at the average accuracy, which shows that the neural tangent kernel is a little bit more accurate than random forests, and more accurate than neural networks, and more accurate than other kinds of kernels like a Gaussian kernel. And so they drew two conclusions from this. One is that the NTK is a good approximation to neural networks, right? That in fact, if you think of NTK as like an infinitely wide neural network, this is showing that if you make the network wider, you actually get somewhat better performance, right? So these are finite width neural networks, and they're pretty good, but they're not as good as the NTK, which is infinitely wide. The other conclusion they drew is that NTK is better than other kernels, and so they suggested that there's really something special about NTK that's making it, that helps them explain why neural networks work so well. And they said that NTK should really become part of the standard toolbox that people use in machine learning. So on the other hand, another experiment had been done by Belkin and his collaborators. And this related to the first experiments I showed you of MNIST with random labels. And what they showed is that they looked at the dynamics of fitting. So I said neural networks are slow to fit these random labels. And they showed that a kernel method with a Laplacian kernel has similar behavior to a neural network. And this suggested that there's some connection between the Laplacian kernel and the neural network. And so going back, you notice that in Aurora's paper, they didn't experiment with a Laplacian kernel. So if we plot the NTK, the Gaussian, and the Laplacian kernel for 1D, this comparison is really striking, right? So the green curve is a Gaussian, which is much smoother. And the NTK and the Laplacian look almost identical. And so as it turns out, so I'm going to describe just a little analysis that shows that in fact, yeah, the neural tangent kernel is very, very similar to a Laplace kernel. And the Laplace kernel, so this is just a general form for the kernels, for exponential kernels in general. And the Gaussian kernel, we have gamma equals 2. For the Laplace kernel, we just have the same thing with gamma equals 1. And so it's much more peaked. And by the way, in general, we're going to call these gamma exponential kernels. So you can have a gamma exponential kernel with any gamma less than 2. So to understand kernels, one way to characterize them is in terms of their reproducing kernel Hilbert space. And so basically, Mercer's theorem says that the kernels can be written as combinations of their eigenvectors. And there's this, and if we understand the RKHS norm, which depends on the eigenvalues of these eigenvectors, we can understand what functions the network can learn. So I'm going to just try to describe this at a high level for lack of time. But basically, with a Gaussian kernel, the eigenvalues decay exponentially. They decay very rapidly. And as a result, the Gaussian kernel can, when we do kernel regression with the Gaussian kernel, we only learn very smooth functions. And what we show is, for the case of data normalized onto the hypersphere, with the Laplace kernel, well, first of all, we've already shown for the NTK that the eigenvalues don't decay exponentially, they decay quadratically. And that means NTK can learn functions that are much less smooth than the Gaussian. And what we show in this work is that the Laplace kernel has the same rate of decay as NTK. And all of these kernels, because they're rotationally symmetric, amount to convolutions, and so they all have the same eigenvectors. The eigenvectors are always the Fourier series of the spherical harmonics. And so the only meaningful difference between them is the eigenvalues. And we show that asymptotically, the eigenvalues of the Laplace kernel and the NTK decay at exactly the same rate. And we also look at deeper networks, but I'll skip over that for now. And this is just giving a little outline of these proofs. And here what we show actually is that the rate of decay of the two-layer network with bias is bounded by two constants in this exponential rate of decay. And with the Laplace kernel, we get basically the same result. So if we plot the eigenvalues of these three different kernels, you can see that the Gaussian eigenvalues decay very rapidly. This is an empirical plot. And the Laplace kernel and the NTK decay asymptotically at the same rate. There's a little bit of difference between them, though, which means that in practice, they may perform a little bit differently. And I just want to quickly show some experiments. So I'll skip over some of this. And so this is the same data set, the UCI data set that had been used in Rohrer's paper, but we also experiment with the Laplace kernel. And the accuracy of the Laplace kernel is pretty close to NTK, but a little bit worse. And I think the reason for this is that when they did these NTK experiments, they had a bunch of parameters they could tune because they considered networks of different layers and they considered some other variables, so they get different NTKs. And so they had more parameter tuning available to them. And so to get a comparable amount of parameter tuning, we looked at the gamma exponential kernel. And so this is like the Laplace kernel, but it's not restricted for gamma to be 1. So there's a little bit more tuning here. And we find that the performance of the gamma exponential kernel is almost exactly the same as NTK. And so it's not clear that this is really, that NTK is a new kernel that needs to be added to the machine learning toolbox, because its performance actually is very close to a well-known existing kernel, the gamma exponential kernel. And we also did some experiments on larger scale data sets using, so this, the trouble with applying kernel methods to very large data sets is that the kernel size is quadratic in the size of the training set. And so there are methods that have been developed using a Nystrom method to approximate these very large kernel matrices. And using that, we also see, I'm skipping over a couple of details here, that basically the gamma exponential and the Laplace kernel and the NTK are all really quite similar, you know, on a bunch of very large scale real world data sets. Okay, so the conclusion of all of this is that there's some empirical evidence that at least fully connected neural networks can be pretty well approximated by kernel methods using the neural tangent kernel, and that the neural tangent kernel itself is really not that different from the Laplace kernel, which is you know, a standard kernel that people have used for a long time. And using, so this suggests that fully connected networks can be analyzed and understood in terms of a very simple classic kernel method. And this can explain a lot of the performance and dynamics of fully connected neural networks. Now, on the one hand, this kind of leads to a rather disappointing message that maybe neural networks are just not all that different from classic approaches. And there's a few caveats to that. I mean, to some extent, our experiments indicate that that's true, but only in certain ways. So one point is that kernel methods have a lot of trouble dealing with large training sets, and neural networks don't have that problem. They can be trained efficiently on large training sets. The second point is that we haven't talked at all about convolutional neural networks. And in fact, when you look at the really dramatic successes of deep learning, they're mostly using convolutional neural networks. And there is comparable work on convolutional neural tangent kernels, and I think that's an interesting direction to try to understand in the future, but it's a lot more complicated. And of course, neural networks are in some sense easier to tune, and you can play around with the architectures much more easily. You can change the loss functions. You can use, you know, GANs. You can connect them to reinforcement learning, and it's not necessarily as easy to do this with kernel methods. And so it's not to say that people should stop using fully connected neural networks and just use the Laplace kernel, but rather that as an analysis tool, understanding this connection between the Laplace kernel and neural networks may make analysis much simpler. That's our hope anyway. Okay, so thanks everybody, and I'm happy to take any questions if there are any.
Thank you so much, David. So I think, and in case people like to upload, you have a reactions button down below. You can click on that one to express your feelings or opinion. Thumbs up and clapping. Thank you. And we have time for questions. We can also stop recording, presumably, and then we do the questions in case people would not like to